Welcome all to this new session, which is going to focus on the planar kinetics equation of motion and rotation about fixed axis. The objectives of this session is to discuss the equations of motion, kinetic moment. We will also consider three situations, which are slipping versus tipping, slipping versus freely rotating, and wheelie versus non-wheelie condition. Now, let's assume that we have a rigid body where there are some forces, F1, F2, F3, and let's say one moment is applied on it. And if we have X and Y as a coordinate, then we can simply write down the equations of motion, which are the Newton's second law. The sum of all forces along X equals to the mass by AgX, and then the sum of all forces along Y equals to the mass by AGY, and then finally the sum of the moment about the center of gravity G equals to IG alpha. Now, if you remember, we said before that this is the free body diagram, which represents the left-hand side of the Newton's second law. There is another diagram, which is called the kinetic diagram, which represents the right-hand side of the Newton's second law. Now, how is this represented? So just assume that this body is the same as this one. And after applying all of these forces and moment, we have the kinetic diagram shown as here. So this rigid body will have its center of gravity right here, and this vector magx is shown here, and this vector magy is shown over here, and this vector ig alpha is shown over here. Now, what is interesting and probably new to you is that we can sum all the moment at a given point, and let's assume that this point is point P, and equate it with the sum of all kinetic moment about P. So what is this kinetic moment? I'm going to describe it and discuss it in the next slide. But basically, just remember that the summation of moment in the free body diagram is equal to the summation of kinetic moment in the kinetic diagram. So let's see how we can write down the kinetic moment. Now, if we consider this kinetic diagram, we have the inertial vectors magx, magy, and ig alpha. And as you see, this vector has a perpendicular distance y bar, while this one has a perpendicular distance x bar from point P. So if we want to write the kinetic moment equation, then let's assume that counterclockwise is positive. Then we sum all of the moment about point P, and we say that this is equal to the kinetic moment. So by inspecting this vector, we can see that it will cause a clockwise rotation, while this one will cause counterclockwise rotation. So what we will have is minus y bar m by agx, because it causes clockwise rotation, plus x bar m agy. Again, this is because it causes counterclockwise rotation, which is positive. And finally, we have ig alpha. So again, what we have here is the sum of all moment about point P, which is equal to the sum of all kinetic moment about P. If a body which is acted upon by different forces and moment end up being translating into a rectilinear path, then this free body diagram would be represented in the kinetic diagram as one acceleration vector acting on the path of the translation, and we can represent this by the sum of all forces along x equals to m a g x, and the sum of all forces y equals to m a g y. And because although we have different forces acting in different direction as well as different moment, but the body ended up translating in a rectilinear path, this means we have no rotation, and for that the sum of the moment about g will be equals to 0. There is no alpha. So this is for the free body diagram right here. Now if I want to write down the kinetic moment, I will have counterclockwise as positive, then the sum of all moment, let's say about point A, is equal to the sum of all kinetic moment about point A. So all what I have to do is to sum all the moment from the forces and from the applied forces and the applied moment and equate it with m a g multiplied by d. What is this? This is basically this vector causing a moment at point A, and we just have to multiply the vector by the perpendicular distance, which is d. Now let's consider curvilinear translation. So again, we have a rigid body. This rigid body is under the effect of many forces and different moments, but it ended up moving in a translation over a curved line. So translation means there is no rotation, and as we know, the translation over curvilinear path will generate normal acceleration component and tangential acceleration component. So the tangential acceleration, which is represented by this vector in the kinetic diagram, this is the kinetic diagram, this is the free body diagram, is MAGT, which is tangent to the path, and it is represented at the center of gravity, and then the normal component is pointing toward the center of the rotation. And as you see, if we assume that we are considering point P, point B has a perpendicular distance, an offset from the tangential acceleration, and it has an offset h from the normal acceleration. So if we want to write down the equations of motion from the free body diagram, then we will say that the sum of all forces acting along the normal direction is equal to the mass multiplied by a gn, which is the normal acceleration, and then we will have the sum of all the forces acting along the tangent equals to the mass multiplied by a g tangential component. And again, since this is a translation, we will have the sum of all moment about the center of mass G is equal to 0. So let's do it again and take the moment at point B and say that this is equal to the sum of all kinetic moment about point B. So if we do this, we have to take the sum of all moment caused by the forces and moment applied on the body as shown in the free body diagram, and then say that this is equal to E multiplied by M A G T minus H multiplied by M A G N. So let me explain this quickly. What we have over here is this inertial vector MAGT, which is shown over here, which has a perpendicular distance with respect to point B as E. So if you look carefully, this is going to cause counterclockwise rotation about point B, and this is why we have it as positive, while the normal component will go this multiplied by H, and this is going to cause a clockwise rotation about B, and this is why we have it as negative. Now let's consider the slipping and tipping cases. If you have a rigid body like this chest drawer and you are pushing on it by a force P to move it to the left, you can imagine that you might have two possibilities here. The first one is that the chest drawer will simply start to slip to the left. The other one is that the chest drawer might tip over and rotate around point A. So how do we know what is going to happen? Well, first of all, before I start showing you how to calculate this, you should understand that if this chest drawer is stationary and static, nobody is pushing it, it's not moving, then the normal force will be acting on the middle, right here. But once the chest drawer is in dynamic mode, this normal force will shift. And the only way to know if this is going to tip or slip is by this calculation. If x is greater than 1.5 feet, then this is considered to be tipping. Or if x is, let me just clear this up, if x is less than 1.5 feet, then this is slipping. So let me explain. Here we are saying that the distance from the middle at the center of gravity to the end of the drawer is 1.5. So this is not shown here clearly, but this distance is 1.5 feet. Now, as I explained, the normal force will shift. So if the normal force was calculated and it was shown to be acting beyond 1.5, so somewhere here, that's impossible. This means the chest drawer already tipped. While if the normal force came out to be acting along this distance somewhere, then this is a situation where we have a slipping. Now let's consider the slipping versus freely rotating case. And let's assume that we have this back wheel drive racing car, which has a center of gravity acting right here, that's mg. We will have two normal forces, NA and NB. Now, if the back wheel happened to slip, then we will have the friction force as Fa equals to mu kNa. And in that situation, we will have the back wheel in a slipping condition, while the front wheel is said to be in a freely rotating condition. Now let's consider the wheelie versus non-wheelie condition. And here we have the same racing car, but at this moment, while the back drive wheel is rotating, the front wheel is lifted off the ground. So if we have that case, then the normal force here is 0. And this is what we call the wheelie condition, which is the situation when the front wheel is lifted off the ground. So let's have this first example where we have a person riding a bike, and we have been given the location of his center of gravity. Also, we have been given the mass of this person, which is 80 kilogram, the coefficient of friction, and what we want is to determine the normal force acting on wheel A and the back wheel B, as well as the acceleration when the rear wheel was locked for brake. So let's start the solution by showing the forces acting on the system, and by the system I mean the person and the bike. So we have mg and we have na and nb. Of course, there was no information given about the mass or the weight of the bike, so it's simply ignored. Now, since the brake was applied, so the wheel at the back was locked, then we will assume that basically the whole system is slipping to the left-hand side, and for that, the friction force is going to act in the opposite direction of the motion, so we will have the friction as mu b n b. Now, what else? We have the acceleration going on the right-hand side because this is deceleration case. Now, we will also have this as the x direction and this one as the y direction. So let's start with the Newton's second law. We'll take the right-hand side as positive, so we will sum up the forces along x. Say this is equal to the mass by agx. And we have only one force acting along the x direction, which is mu b and b. And for this, we will have 0.8, which is the coefficient of friction, multiplied by nb, and this is equal to the mass, which is 80 kilogram, multiplied by ag. Now, I didn't say agx, and the reason here is that there is no motion along the y direction, so we will have only one component of acceleration along the x direction. Now, we have also chosen up as positive, and then we sum of the forces along y. Now, this is m-a-g-y, which I said it is 0. So we will have nb plus na minus 80 multiplied by 9.81, which is equal to 0. So for the third equation, we are going to write down the kinetic moment at point A, right here. So as I described before, we will take the counterclockwise as positive, and then we will sum up the moment about A, and say that this is equal to the sum of all kinetic moment about A. Now, we have here this force, NB, at a distance 0.95, causing a counterclockwise rotation, and we have mg causing a clockwise rotation, and it is at a distance of 0.55. Now, so what I will have NB multiplied by 0.95 minus 80 multiplied by 9.81 multiplied by 0.55. And all of this is equal to the acceleration by the mass multiplied by the distance, which is this 1.2. And as we see, this is also causing a clockwise rotation. So I will end up having minus 80 AG multiplied by 1.2. If I solve all of the three equations, this is equation number 1, this is equation number 2, and this is equation number 3, I will get AG equal to 2.26 meter per second square, NB equals to 226 Newton, and NA equals to 559 Newton. Now let's reconsider the person and the bike, but at this time we are only requested to identify the forces and the acceleration when this person is traveling at a constant velocity and no brake was applied. Now what we will have here is the weight, that's mg, and also we will have the normal forces at A and the normal force at B. Now since this is moving at a constant velocity at the left, but the acceleration AG is going to be 0 because the velocity is constant. Now the only force that remains is the friction force. Now since we know that as the bike is moving forward, the wheel is moving at this direction, so at this instant the friction force is going to go in the opposite direction of the motion, which is mu p n b. Now in this other example, we are again requested to identify the forces and the acceleration when the rider applies the front brake and the back wheel start to lift off the ground. So again, we should show the weight mg, and we will have NA as a normal force, and at this time NB is going to be 0. Now since the brake was applied, then we understand that this is going to be a decelerating system, so the acceleration will go to the right while the bike and the rider is still moving to the left. And because of that, the friction force is going to act in the opposite sense of the motion, and we will have mu k NA acting this way. The last example is shown here, and for this we have a 100 kilogram beam BD. So this is the beam which has a mass of 100 kilogram, and it is supported by 2 rods, but these 2 rods has negligible mass. We want to determine the force developed in each rod if at the instant when theta equals to 30, and this is theta equals to 30, omega equals to 6 radian per second. So let's start by showing the free body diagram for both the beam and the rod. Now for the beam has mass of 100 kilogram multiplied by the gravitational acceleration you will get 981 Newton acting downward. The two rod will act as if there are two forces. We will call one as TD and the other one as TB. And since this is rotating, we will have a normal tangential coordinate. And for the rod here, also, since this is rotating, we will have point B rotating about point A, and at this point we will have two components of acceleration, tangential and normal. Omega was given as 6 radian per second. So we will start writing the equations of motion along the normal and tangential coordinates. So let's just start with the normal component. So taking this direction as positive, we sum the forces along the normal, and we say that this is equal to MAG along the normal. And what is this going to give you? It is going to give you TB plus TD minus 981 cosine 30. And this is equal to 100 kilogram multiplied by 18 meter per second square. Let me explain those terms. So first, we have the TB acting along the normal direction, no problem. TD also acting along the normal direction. For the weight, if we want to show it, then we will have the normal component of the weight acting this way and its tangential component acting that way. This is the 30. So what we have over here is the cosine, which is this component, and it is negative because this is the direction of positive and this is the direction where it is supposed to be negative. Now this is equal to M, which is the mass, by A normal. Now the normal component, if you remember, A n is equal to omega square r for rigid body. Now omega is 6, so 6 square is 36 multiplied by r, which is 0.5. This will give you 18. So this 18 is the normal acceleration. Now let's move on to the tangential component. For the tangential component, we will take this as positive, and we will have the sum of Ft is equal to MAGT. And for this, we will have 981 multiplied by sine 30. And this is equal to 100 kilogram multiplied by AGT. And again, let me explain. So we have here, this is the tangential component of the weight acting in the same direction as positive t. And what we also have is the mass and the tangential component of acceleration, which is unknown. Of course, since these act along the normal direction, they will not have any component along the tangential direction. Now, let's move on to the moment. So we take the moment as a counterclockwise is positive, and we sum it about point G. And we say that this is equal to 0. The reason why is that since omega was given to us as 6 radian per second at that instant, then it is constant, and alpha is going to be 0. So we now sum up the tangential, we sum up the moment, so we have minus TB cosine 30 multiplied by 0.4 plus TD cosine 30 multiplied by 0.4, which is equal to 0. So if I want to explain this, this is TB, and we are taking its cosine, so its cosine component is this one, and we are multiplying it by 0.4. Now clearly, if you have this component and this one, so this component will cause rotation, which is about g, which is clockwise, and this is why it is negative. While if you look at the component of TD, then what we will have is this force, which is also the cosine 30 of this, but this one is going in a counterclockwise with respect to g, and this is why it is positive. By solving the three equations, we will get TB equals to TD, which is equal to 1.32 kilonewton, and we will get AG tangential equals to 4.905 meter per second square. So in summary, we have discussed the rule of the center of mass G. We also explained the equations of motion for rectilinear, curvilinear path. We discussed the kinetic moment. We have discussed also the slipping, tipping, freely rotating wheelie, and non-wheelie conditions. That's it. Thank you.